Let's dive into the world of video and video streaming, and our next speaker, Ilya Mikhaelis, will tell us more about that and really deep. Please welcome Ilya. The stage is yours.
Thank you. Thank you. So today's topic is WebRTC, and before we start, I want to introduce myself. My name is Ilya. All my career, I have been developing streaming solutions. Some of them was good, some of them no, but anyway, our team currently develops media live streaming CDN. And the main problem with live content is latency. Waiting for an answer to a simple question for 5 to 10 seconds is annoying and kill all live in communication. Don't you think so? And this is typical latency values for the most popular nowadays protocols like, oh my God, HLS or Dash. But here we have a game changer, which is called WebRTC. WebRTC is a quite new technology which allows to connect peers with sub-second latency. It means that latency will be lower than a second. But why in most cases streams are distorted and frozen? How to overcome these problems? In my speech, you will find answers to these questions and even more. And today's plan is the following. First of all, we will revise the theory of video streaming, which is necessary for the next section, which is called WebRTC Technical Overview. Then we have the most interesting part, and it is troubleshooting. And in the end, we have a few words about the results. And the first question would be, what is video? If you think that video is just a sequence of images followed one by one individually, you will be close, but everything is more complicated. For example, if we take stream, full HD stream with 30 frames per second, and in this model calculate bitrate, it will be 1.5 gigabit per second. Of course, it is an enormous value that can be distributed via public network. That's why people have invented several optimizations, and the first one is frame types. And all frames along the stream may be split into two groups. The first one is called I or key or intro frame, and this group represents the whole picture. And the second one is called forward predicted frames or diffs applied to this picture one by one, consequently. And by this optimization, you may achieve lower size of diffs because it's just a diffs to the whole picture. And such a pattern, like the whole frame and diffs applied to this picture, is called GOP or group of pictures. And we have more complex optimization, which is called bidirectional frame. These frames has less size than just P frames, and they are diffs to the previous picture and the next one. That's why they call bidirectional. OK, now I want to show you how this optimization works in real life. And I have prepared several streams for you. All of these streams have the same capabilities. They have the same codec, the same bitrate, the same resolution, and the same frame rate, but different frame types optimization. So let's watch. You will find several differences. We will discuss them later. And the first one, stream with only iframes inside. So as you may notice, picture looks terrible. Yeah? A lot of pixelization on the screen, very bad stream. OK, now we may apply all this optimization. I mean, we have a GOP with I, P, and B frames inside. The same bitrate, the same resolution, and the same frame rate. Let's watch. Much better, you see. The picture looks smooth. Everything is perfect. Very good. OK. And I have a comparison, both of these streams in one picture. So you may find that there is a lot of artifacts, especially on the borders of the objects, and this is how this optimization works in real life. But this optimization has a limitation, and I will show you. This stream contains artifacts with which you have faced at least once in your lives when you have a Zoom call or Google Meet call, for example. Let's watch. Aha, you see, yeah? A lot of artifacts, and then picture is restored again, and then again restored. OK, and what is the problem? The problem is inside our model. If we drop some P frame inside the group of picture, further diffs, further P frames will be applied in wrong positions. That's why we have such artifacts on the screen. And after new iframe, which is in red color, iframe is the whole picture. That's why the screen is restored. and so on. Everything is perfect, p-frames applied in the right directions, right positions, and so on. And after all these frame types optimizations, we may compress stream with some algorithm, which is called codec. For example, the most popular nowadays and the most widely spread all over the world codec is H.264. It's, of course, for video. And if you apply all frame types optimizations and all codecs optimization to the stream, which we will discussed earlier with the 1.5 gigabit, we may achieve quite good level of compression to 8 to 10 megabits per second. And this is typical latency values for the most popular TV Netflix series, for example, in full HD quality. Codecs is a difficult topic with a lot of math inside, so they're out of my speech. But anyway, we have enough knowledge to move forward and speak about WebRTC. And the first question will be again, what is WebRTC? WebRTC is a technology which was developed in 2011, but it was standardized only in 2021. It has a lot of advantages, except low latency. It is supported by all well-known browsers like Firefox, Chrome, Safari. And all of these browsers provide a simple API, front-end API. It means that any front-end developer may implement Zoom clone by the end of the day. It sounds I need to end my speech here, but everything is more complicated. Especially if you want to create one-to-many or many-to-many conferences. You can't deal without middle server. And where to find such middle server? You have several options for that. The first one, you may buy it, or you may try open source solutions, or even implement your own. So let's start from the very beginning. And complete solutions has also several options. And the first one is low latency CDN. But unfortunately, they're extremely expensive, especially for greedy people like our team. So let's say we have 9,000 incoming streams and 100,000 outgoing streams. We will pay $500,000 per month. This is big value. So moreover, such solution has more disadvantages. First of all, except it is too expensive, it doesn't support critical features like transcoding or ABR. That's why you may implement your own CDN based on the closed source solutions, some media servers. But unfortunately, to be honest, we have tried such solution, and unfortunately, they badly performed during high load hours, and they had a long cycle of feature implementing and bug fixing. That's why we decided to get rid of them. And we take a look closer to open source market. And at this time, the most popular open source solution was LibWebRTC, which is a part of Chrome engine. And unfortunately, it was designed as a client library with only one goal, to receive stream whatever it takes. That's why on each peer connection, WebRTC connection, it produces enormous amount of threads. Some of these threads are real-time threads. And that's why if you want to use it on the server side, you will suffer from enormous amount of context switching, your server will lag, and so on. And that's why you need to deeply refactor it. And moreover, you will suffer from each merge conflicts after each trunk update. So you may try another open source solutions. And nowadays, according to benchmarks, Open Media Engine shows quite good performance results. But at the time we started our journey, it hadn't been production ready. It produces big latency, especially on the transcoding. So we decided to not use it. And currently, I don't know its status, so it needs to be checked. Just a hint for you. OK, after all this suffering, we realized that we don't understand how WebRTC works. And there is only one way for engineer to understand how something works, is to implement Bicycle by his own. That's why we decided to implement our own WebRTC library. And WebRTC was a technology which allows peers connect all over the world with some second latency and so on, so on, so on. But what it means from the technical point of view. And from the technical point of view, it means that each of these peers may be in private networks. It may have different devices. It means that they have different encoder and decoder possible configurations. Moreover, they don't know their public address and ports. And these peers must exchange with this information. Moreover, they must keep the public address and ports in network address transfer table, and this phase is called signaling phase in WebRTC. And unfortunately, WebRTC doesn't have any standard for signaling phase. That's why such powerful utilities like FFmpeg or OBS Studio doesn't support WebRTC at all. But just for your information, in nearest future, we have two possible standards, both of them based on the HTTP. And the first one is called WHIP for injecting stream to the remote peer. And the second one is called WHIP for receiving stream from the remote peer. But let's look closer to our case. We have a public server with public IP address, and we have a client which, for example, decided to receive stream. And we will use HTTP for signaling protocol. And at this point, client doesn't know its public address and port. It sends its possible video and audio decoder configurations. Let's say, in my case, it will be H.264 and VP8 for video and Opus for audio. And server matches these configurations with possible server configurations. It selected H.264 and Opus in my case, and responds it with selected configurations, and also states IP address and port on which it will listen for WebRTC connection. After that, we have some kind of a magic inside browsers, and in a few seconds, we started to receive stream. So let's go deeper and understand what is under this magic. And before we start, I want to add that in spite of fact we don't have a signaling protocol standard, we have a requirement how this configuration must be described, and it is called session description protocol. And this is typical from SDP, from the client device. And what we have here two sections, one for audio, one for video, with possible codecs like Opus or H.264 and VP8 for video. Also some credentials and some magic lines which we will discuss earlier. And to be more precise with WebRTC terms, I want to add that when you send SDP to the remote peer, in our case it is server, it is called SDP offer. And when you answer with the SDP, it is called SDP answer, and this is common terms of WebRTC technology. And after that, we have a phase which is called ICE, or Interactive Connection Establishment. And ICE is a technology which is used in WebRTC. And at this point, client may have different interfaces. It may have Ethernet, VPN, Wi-Fi, and so on. And for this purpose, client starts to send STAN bind requests. STAN is a protocol which is used for connection establishment. Each of these datagrams, STAN datagrams, contains credentials from the SDPs, both of these peers, client and server. And the server handles all these bind requests from all the interfaces of the client, and responses with bind replies with also stated credentials from the SDPs. By these credentials, server and client understands that this is known client or known server. And after that, client, after client received all these responses, it may, for example, select the most suitable route for media traffic, for example, by RTT, and again send bind request from the selected interface to the server. At this point, server knows on which interface, on which address client will listen for media traffic. And for media traffic, WebRTC uses quite old protocol, which was designed in 1996, and it is called RTP, or real-time protocol. In most cases, it works over UDP, and it also has a codec-specific supported part, which is called real-time control protocol, which is used for quality of service and audio-video synchronization. And I want to add that RTP is a codec-specific protocol. It means only specific codec can be sent through the server. It is a disadvantage of it. And for my case, it must be H.264 and Opus for audio. And I have skipped one more phase. Of course, browsers can deal without encryption. And this phase located between ICE and media. This is out of the browser's policy to deal with unencrypted traffic. That's why WebRTC has an encryption phase, and it is made a little bit tricky. First of all the RTP and RTCP payloads encrypted with AES cipher, but how to exchange keys and certificates? For this purpose, WebRTC uses DTLS protocol. And we have an assumption, because after we exchange with certificates and keys, we calculate the address from them, and we need to compare it with SDP fingerprints. And that's why we have an assumption that browsers or remote peers trust to any signaling protocol which is used for communication. OK, it was a boring part. Sorry. And now we have enough knowledges. We became professionals in WebRTC and media streaming. That's why we may have a troubleshooting section. And the first problem will be the most obvious one, because WebRTC in most cases works over UDP. And UDP doesn't have any guarantee about receiving packets and so on. That's why we will have packet loss. And the more quality you have, for example, you have 4K, the more bit rate you have, it means that your frame will consist of more packets, and the more packets, the more probability of packet loss. And there is only one packet is enough to drop the whole frame, because decoders can't deal with unfinished frames. And as you know earlier, because you are professionals, only one frame is enough to corrupt the whole group of picture. That's why you will have artifacts on the screen, and unfortunately, this is how real life works. But hopefully, WebRTC has several techniques how to recover from such problems. And the first one is called negative acknowledgement feedback, or NAC. It is sent over a TCP part of WebRTC. And in simple words, it's just a small datagram which contains a sequence number of lost datagrams. And on the remote side, on the server side, you may ignore such request, or you may resend lost datagrams. And if you control both sides, client and server, you control datagram cache, you may achieve quite good stability of the stream. And you will find support negative acknowledgement feedback inside your SDP. For example, in my server SDP, I have NAC support for H.264 video stream. To be honest, WebRTC has more solutions for recovering from such problems, and both of them based on the information redundancy inside packets. And the first one is called forward error correction, and the second one is called redundancy data. And in simple words, FEC, it's just when you add redundant information to the packet about its neighbors. So it means that if I lost packet in the middle, I may reassemble it from the packet from its left and right side. And red, it's just a duplication, the same packets. It means that you may use red for audio instead of video, because video traffic is really heavy. But it is like a hint. You may decide by your own. And in the end, I want to add that if you had a big RTT, you'd better to use FEC, increased information redundancy, instead of NAC, because if you want to avoid latency and increase stream stability, better to use FEC. But you will pay by traffic, of course. And the second problem is the following. As Nick Shadrin mentioned before in his talk, some of public networks doesn't allow traffic from except standard ports like 443, 80, or 9035, for example. Moreover, some internet providers ban UDP traffic. Especially, it was a common practice before the pandemic in European countries. And how to deal with that? And for this purpose, WebRTC hopefully has an answer. You may state several address and ports on which you will listen for WebRTC connection, for example, in your server side. And some of them may be on the UDP, some of them may be on the TCP, and moreover, they may be on the one port, for example, 443. And you may also play with priorities. And the more priority you have, the more preferable address is. And for example, you may set the highest priority for UDP address and lower priority for TCP. That's why customers that don't have any problems with their network, they will use UDP, and they will enjoy live low latency streaming over UDP. customers which have problem with UDP will continue enjoy streaming over TCP, yet they may have a little bit latency because of the poor network, for example, but anyway, it is better than staring at black screen. And the next problem is the following. It is a little bit difficult. Imagine you have a customer which streams over your CDN, and this customer also has a website which is distributed over your CDN, and he has the following complaint. On his preview, for example, on his browser or some tool, everything is perfect, but his customers on his website observe black screen. And what is the problem? And we need to go backward to the theory. Do you remember that we have iframes and pframes that are diffs applied to this iframe? And when you don't have iframe, when your decoder don't have iframe, it can't deal with pframes because there is no picture to which it may apply these diffs. That's why it started to just drop them and until next iframe. And unfortunately, there is no requirement how frequently iframes must be occurred in the stream. That's why we have different devices, different browsers, and so on, and there is no requirement. So that's why customers observe back screen, because on some devices it may be 2 seconds between iframes, on other devices it may be 2 hours, and so on. And how to overcome this? WebRTC has again solution for that, and again it must be sent over RTCP feedback, and it is called picture loss indicator. This feedback is sent from the server, and client publish stream to our server. And this feedback is sent from the server, and it means that client should generate iframe and send it back to the server. And now you may implement logic whatever you like. For example, you may send picture loss indicator each 2 seconds, or you may send picture loss indicator each new customer connected to your stream. And you may find support of picture loss indicator inside the remote peer SDP. For example, for my server, I have support for picture loss indicator for H.264 stream. And the last problem is the most interesting one and the most difficult, I think. Imagine the following situation that, again, the same customer distributed his stream through your CDN and also his site. And he has again the complaint, but with the following text. That in his OBS preview, everything is perfect. Stream is beautiful. But on his site, stream is joking all the time. What is the problem? And I have prepared a video to show you how it looks like. OK, let's watch. You see. You may have mental disorder at the end of this stream. OK. And we need to go backward to the theory. Remember, we have a group of pictures with iframe and diffs inside. And to be honest, each frame has the following capability connected with time, which is called presentation timestamps and decode timestamps. And the presentation timestamps, or PTS, it is a capability when this frame must be displayed on the screen. And DTS is a capability when this frame must be decoded. And DTS must monotonically increased. And when you don't have B frames, everything is simple. Display order equals to decode order, PTS equals to DTS, everything is simple. But when you have B frames, it means that you have diffs to the previous and the next one. Your display order doesn't equal to decode order. You have reorderings, you have some bufferings on the client side. And this is not supported by default in WebRTC technology. That's why WebRTC cut off information according to PTS from all the frames. Moreover, on the RTP part, it supports only one timestamp, and it is DTS. That's why you lost display order, and that's why you display your frames in the wrong order. That's why you have such joking. And how to overcome this? You have, let's say, 2 options. The first one is to forbid to broadcast with B frames, but it is almost impossible because streamers like their OBS studio, they like settings that it have, and so on. So it's almost impossible. You may try to transcode such streams. It means to decode, find all B frames, change them to P frames, and encode again. But it consumes a lot of resources, so it is kind of trade-off you need to decide by your own. And as I promised, I have a few words about our results, only one slide. We started our journey from closed solution on Java, and during high load periods, we suffer from performance problems, our streams distort and frozen. After that, we decided to implement our own WebRTC library written in C++, and finally we achieved extremely good performance boost from 80% of CPU load to only 20%, and we started to control NAC, FEC, and ABR techniques, and after that, quality of pictures in our streams became much better. So that's it. I hope you haven't been so boring by my speech. Thank you very much, and I'm ready to answer your questions.
Thank you. Thank you very much, Ilya. Don't forget to rate the talk. Please scan the QR code. We have plenty of people here. So, any questions? Raise your hands. A question to the left side from me, please. Raise your hands if you have any more questions so I can see you.
Hello, my name is Sergey, and my question is about B-frames problem that you gave us two solutions, both of them are bad, actually, and how did you solve this problem?
We decided to transcode because there is no good option for that. Unfortunately, you can't deal with that, and for my opinion, the best solution that we have nowadays is just to transcode. Yes, we will pay by money, by resources, but it's kind of trade-off.
So what was solved your issue, yeah, finally? C++ instead of Java, or WebRTC with its great future? What do you think?
By the way, you need to understand that Java is a good language, and there is no complaints about Java. You know, it's a difficult question because maybe in high-load systems it is better to use C++, but if you speak about fast solutions, we need to implement something fast. Java is much better, of course. And to be honest, nowadays Java performs quite good anyway. But it is difficult to cook it, I think, on the DevOps side, maybe on something like that, and even in code, maybe. And in our case, I would say that, by the way, Java solution was also works with WebRTC. And in our case, I will say that, of course, it was C++, and not because of language, but because of high-quality professionals that work in our team. And the second option, I will say that, the second point, that we started to understood deeply how WebRTC works and how to cook it with FEC, ABR techniques, NEX, and this is the reason, I think. I hope I answered.
Hello, thank you for your report. You have told that you faced that some companies or providers block UDP traffic, and you faced the problem that some companies block any other ports except 443, and have you fixed it, and can you work with it?
Yeah. As I mentioned before, you may have several addresses on which you will listen and send media traffic. Some of them may be on TCP, some of them may be on UDP. It is okay. And they also may be on the same port, for example, 443, the standard port, which is opened in all, I think, networks. And this is the solution. So you may try it.
So a decision can do this, yes?
Yeah, no problem.
And the second question, you compared your solution with Java decision, and you compared your solution with some decision on Go that was implemented from the zero, as you do.
It is a good question, and I won't lie to you, because I don't. maybe because there is no good solution on Go on the open market, because well-known solutions. Because most of the streaming solution nowadays written in Java.
No, not all.
No,
We'll
okay.
discuss,
The most popular, I would say, Wolves, for example, or something like that, Unreal Media Engine. And they perform, in my opinion, not good. But in Go, I would say no, I don't know.
It works good.
Hopefully, sounds good.
Thank you.
Thank you. Yes, gentleman over here.
Thank you. I have just a little question. How does WebRTC differ from other live streaming protocols in terms of latency?
You mean how does performance in terms of latency? Yeah. Let's say on the open source solutions, open source protocols, WebRTC the best one, I think. You have, for example, low latency HLS, which is designed by Apple, but still it's more stable, I think, but it produces latency because you know it's kind of trade-off. You need some buffering to make streams more stable, but at the same time you want to have small latency, and you need to decide. And when you have browsers, it is difficult to set them correct amount of buffer. That's why in most cases, if you don't cook WebRTC properly, you don't properly set up NAC or FEC, you will have some artifacts on the screen. And you won't observe such history in HLS, for example. But still, the best latency is for WebRTC, I think.
Thank you.
We have a question on the left.
Hi. Does WebRTC suitable for peer-to-peer streaming or only for like central server?
No. WebRTC was designed for P2P, by the way, peer-to-peer, yeah. But nowadays, it is more popular to use it as a server solution because it's like kind of a race between technologies to achieve the lowest latency. For example, in cloud gaming, or education, and so on. VR, for example. That's why more and more WebRTC is used in server solutions.
In the beginning, you mentioned that you can create solution based on CDN, yeah, but it will be expensive, yeah. So have your custom solution helped you to reduce network cost, for example, to deliver video streams between client and servers?
Yeah. As I understood right, it is quite new technology. That's why CDNs are very expensive. There is a few CDNs that allows to stream WebRTC because it doesn't support caching. It is a push model. For example, HLS is a pull model when you have small files and so on. That's why it's so expensive. So we decided to build our own CDN, and of course it is more cheaper for us, for our company, than use some external CDNs. Yes, we have some benefit in money, but I think I can't say the right values because it's a commercial secret, I think. That's why.
Hello, that's me again. I have one quick question. Do you plan to open source your solution?
Very good question. I would say yes, but we need to think deeply because we have some technologies inside WebRTC which is supported by, but only by us. For example, we have fast streaming, we have some transcoding. Fast streaming, I mean, when you start stream it, it is push model, but anyway, it starts very fast, lower than a second. And I think some part of our solution will be in open source market. And for me, like a developer, I think open source is a good opportunity to develop our solution. And I hope that, yes, we will do it. But again, it is out of my, let's say, I can't make such decisions because it's a business, you know how it works.
Any more questions? Please raise your hand. Maybe behind the pillar where you can yes, to the left we have two questions.
Yeah, another one question, not really about WebRTC, but well, you mentioned about UDP ban by providers, and you said that it was pretty popular before the pandemic. So, is it? Does it changes?
Yes,
yeah.
I understood question, sorry. Yes, especially before pandemic, because people like to interact each other and through Zoom, for example, through Google Meet. And moreover, we have HTTP 3, as you know, and it also works in most cases, not in most cases, in all cases over UDP. And after that, providers realize that why they should ban UDP, because everything tries to move to UDP. That's why nowadays, yes, this history is much more easier and popular. So yes, we have some. But anyway, we have already solved this problem, though. So that's it.
Okay, I thought we had two questions there. There was only one. Any more? Please raise your hands. Yes, gentleman in front.
Thank you. Is it WebRTC intended for using only for video streaming, or we can stream some binary data or like JSON?
I think it is not suitable for JSON, but WebRTC has data channels. It is called because by design, it was like a simple clone of Skype, for example, technology, yeah, and you may send through data channels, for example, chat, or even commands for some, I think, devices. So yes, it has such an opportunity, and it is used, for example, in Google Meets, they send something through data channels, as I think, so yes, you may. But the main goal of this technology is video and audio, of course.
Any more? Please raise your hand. We have a pair of socks for you if you will ask the best question. Let me remind you. I will try my best to win these socks.
Okay.
So
I will give mine to you.
regarding history of WebRTC, if I know correctly, it's designed by community, by ATF, and there are RFCs about it. And you told about this sort of negotiation. So I have UDP port 25, I have TCP port 33, and then another kind of negotiation. And then comes encryption. And as far as I remember, TLS has all these kind of negotiations as well. So why can't we, or were there any ideas about reusing TLS and its extensions? Maybe we can write another one to use this one and just to shorten our path in this negotiation.
TLS is used for TCP traffic, and in WebRTC they use DTLS. It is for UDP, but they tried to be honest, there was an old technology which RTP was SRTP, and they need the opportunity to roll this protocol to the browser, and nothing to change, just roll this protocol to browser. And how to exchange these keys and certificates and so on? Let's use DTLS, just for exchanging keys and certificates. And wrote SRTP, so from technologies, it is just a combination of protocols, WebRTC, and that's it, from the server side. From the front-end side, it is more difficult because it allows to transcode, capture screen, and so on, but it's like let's say it's not about the protocols, it's about how to use browser.
Thank you. Any more hands? Yes, please.
Hi, thank you
Hi.
for the talk. Just, I'm curious, back to the C++ versus Java versus Go. Does the garbage collection in Java or Go or whatever, does the garbage collector affect a lot the performance?
Good question.
Is it a factor to consider?
Yeah. Before we moved to the last version of garbage collector, it was disgusting because we suffer all the day. And after we moved, we also moved to some. I'm not well familiar with Java, but they have a special API for sockets, as I know. Yeah, and we moved to this API as well. It became better, but still. I think it is more about the quality of software that was written in Java than Java as well. So I hope you understand.
So let's blame developers.
Yeah. By the way, you may have bad solutions in C++ too, and sometimes we have. Yeah.
Yes, another question over there.
Yep. As you said, the WebRTC protocol is some kind of old. It was developed in 2011. Did you make some modifications to protocol to make it better for your solution? Except you said too fast.
Yeah, I understood. To be honest, no, because we need to handle this protocol inside browsers, so we can't change it. If we have an application, yes, but now we have browsers as the end of the as a remote peer for us. That's why we need to keep it as is. But we can control some like NAC, ABR, fast start, and so on.
There is no opportunity in this protocol to make some.
There is a small opportunity which is called, as I remember, extension. You may set some extension, but again, it is difficult for browsers, as I understood, and better to say no.
Thank you. Any more hands? 1, 2, 3. Yes, please.
Thank you. Are there audio codecs except of Opus are handled? Maybe some Google closed codecs that can be handled by browser?
Okay. You mean how they handled by browser or server?
Or server.
By the way, between servers, we also use WebRTC, and we may handle all codecs what we have. For example, we have AAC because quality of AAC is much better than Opus in most cases. But on the external side, I mean, for remote peers, we use Opus. It is a standard for audio in WebRTC.
Thank you. I just heard that Google uses their own Lyra in their Google Meet. And it's
maybe, but we use Opus. So I think I'm not. I can't answer your. I can't have answer better than I said.
Thank you.
Another race hold. Yeah.
Thank you for the talk. It was very interesting. I was wondering if anyone still uses WebRTC for the peer-to-peer communications. You said it was designed for peer-to-peer, but it's now mostly used for the servers.
No. For example, if you have Google Meet with your friend, for example, it will use, I think, peer-to-peer in most cases. Yeah, but if you have more than one, I think it will be through server.
Thank
so
you.
It's okay for more on the open source market. Some of the solutions they based on the peer-to-peer communication, not without a server.
All right then. So, Ilya, choose the best guy.
I forgot everybody. So let's give this guy all the presents because I always watched him. Sorry, guys.
Yes. So, round of applause. Ilya, thank you very much.
Thank you.